Hello, I am Jinho, a student from Georgia Tech. And today I will introduce our open source toolbox AVPASS and our approach for automatically bypassing Android malware detection system. I'm studying in SS Lab from Georgia Tech, and we are focusing on system and security research. And this project is joint work with ISTC ARSI, and this center is focusing on strengthening malware detection systems. In this talk, we will introduce our toolbox of AVPASS, and the key idea of AVPASS is that the AVPASS can transform any Android malware to bypass antivirus softwares. First, by inferring AV features and rules, and by obfuscating Android binary automatically. At the same time, AVPASS try to preventing code leakage problem. As you can see from the figure on the left, Android dominates mobile operating system market. This year, last year, about 80% of a mobile device use Android operating system. And as a result, Android malware become more prevalent. So every day, about 8,400 new Android malware is generated, and security experts expect about 3.5 million new Android malware will be developed in this year. So question, how to protect your mobile device from the malware, so many malwares? So of course, one solution could be using antivirus solution, and there are more than 50 antivirus softwares out there. Unfortunately, antivirus solutions are known to be weak. This slide is taken from the last year DEF CON, and this researcher argued that he uploaded one exploit from the 2012 to the antivirus solution in 2014 and 2016 respectively. More than 50% of antivirus detected it as a malicious. However, this researcher argues that after they modified original exploit a little bit, they said they could successfully bypass the antivirus systems. What about Android malware? The malware goes into the antivirus, and antivirus detected it as a malicious software. This is a good story. And this is our question. How easy to bypass AV software while maintaining the original behavior? Since we don't know anything about the internal of antivirus solutions, there are several challenges. First, we needed to transform the original malware without destroying malicious features. And we don't have enough knowledge about the AV features and its detection logic inside. And finally, we still wanted to prevent code leakage problem when querying to the antivirus solution, because once you get detected by the AV companies, they will share your code among the security community. Here's our approach. We obfuscate individual feature first, and we infer the AV's feature and detect rule combinations of AVs. And then, by using the inferred features and rules, we could successfully bypass most of AVs. And at the same time, we minimize information leakage by sending fake malware, not the original one. This is a summary of our AVPASS operation. AVPASS could bypass most of AVs with 5.8% of detections. And AVPASS discovered 10 features of AVs, and also discovered the bypassing rule combinations, which is about 30% of all possible rule variations. And at the same time, we suggested one way to prevent code leakage when querying by using our imitation mode. This figure shows our overview of our approach. We started from binary obfuscation, and once we make the APK to the obfuscated one, we try to infer the feature and rules by sending the obfuscated binary to the antivirus system. And with the help of a safe query, the malware developer can get the disguised application and then finally can bypass the antivirus. Let's start from the binary obfuscation. What is binary obfuscation? Now you are looking at malware. So as you already know, malicious software has many suspicious signatures inside, such as defined method name, API, and class name, and string variable. After we apply obfuscation, we can generate something that looks different application, but while maintaining the same behavior inside. These are the list of main obfuscating features that we provide. Some of the features are overlapped with commercial solutions, but some of the features are only provided by AVPASS. We cannot just obfuscate binary. There are several requirements, and let me tell you two main requirements for the obfuscation. We need to ensure APK's original functionalities. And obfuscation should be difficult to deobfuscate or reverse, because if it is easy to reverse, the AV companies can analyze original intention easily. This example shows some cases with code injection in the Smiley level. The number in the red box shows the maximum number of registers inside of a method. Original method has 4 number of registers, and we wanted to inject code, and it requires 1 more register. Since the 4 and 5 is a relatively small number, so we can just increase the maximum number of registers and then inject our code. However, this is a tricky problem. Register already, this method uses 4 registers, and because of the parameters, 10 more registers has used. So now total 14 register has used before. And we wanted to inject code, which requires 3 more registers here. Now the maximum number of registers become 17. However, since several instructions only support maximum number of 16 registers, system crashes. We cannot inject code here. And we observed that this situation happens frequently. So to overcome this problem, we traced the register type before the injection point. We back up the register to the temporal place, and we inject the code. After code injection, recover the register by using correct instructions. Other than this example, there are several minor cases we observed, and AVPASS has wrapper function to provide you code, inject code easily. Now move on to the different topic. I mentioned that difficult to reverse obfuscation is important, and some researchers can argue that obfuscation is too easy to detect, right? We agree, true, but it doesn't help AVs much because it's difficult to tell benign or malicious. Difficult to tell original intention of obfuscation. And the other point, dynamic analysis can detect original behavior. However, code coverage is another challenge, and overhead is already known issues of dynamic analysis. This example shows difficult to reverse obfuscation. This example only uses 2 different modules of AVPASS. One is Java reflection, the other is string encryption. This is one simple code snippet. First, Java reflection hides all the API names by using a reflection wrapper, and original string changed into string wrapper with the encrypted key and encrypted message and decryption key. As you can see from here, all the reflection wrapper has the original name of a class and original name of a method. Again, we obfuscate the name by using all different string encryptor. And then again, we encrypt the encrypted string one more time. Now, you can tell obfuscation here, obviously, but you cannot tell the original intention easily. Now let's start from bypassing well-known detection techniques. Since we don't have knowledge about the antivirus solution, we started to bypass these techniques that we can analyze internal detection logic. This is an example that we use to introduce how to bypass the classifier. This malware has two different components. One is broadcast receiver and the other is service. Every time SMS message is received, this broadcast receiver intercepts message and send it to the background service. And then finally, malicious send them the SMS message to the malicious site. How to detect this malware? If you use API-based detection technique, you can look at the suspicious API sequences. And if there is any suspicious sequence found, you can tell that, oh, it is malicious. What about data flow-based technique? First, it identifies all the suspicious source, all the suspicious sync API. If there is any data flow between suspicious source and the sync, it classified it as a malicious software. Component-based detection or interaction-based detection look at the relationship between components. Here, there are two components. One is broadcast receiver, the other is service. If there is suspicious components and data flow between them, it classifies it as a malware. And signature-based detection is famous, and it tries to match any pattern with predefined signatures. How to bypass an API-based system? There are several subcategories of API-based system. If the analysis considers frequency, we can inject massive number of API to make different API frequency. If the analysis considers and monitors the n-gram, in other words, the sequence important, we can insert API between all the existing APIs. Or if the analysis considers API transition ratio important, we can make different transition ratio by changing the package name or class name to our predefined name. This example shows how to break n-gram analysis. As you can see, these three APIs are found as suspicious. But once we inject dummy API between the all existing API, we can break the n-gram analysis. And how to break the transition ratio analysis? This analysis defined user-defined API to string to user-defined as suspicious. And once we move the older user-defined API to the Java util API or Android util API, we could bypass the classifier. To break the data flow based detection system, we could insert the anti-data flow analysis code, which changes explicit data flow into the implicit flow. And to bypass the data flow analysis with different ways, we also can use Java reflection. By using the Java reflection, we can hide all the existing API names and change it into the reflection wrapper. So it means data flow analysis cannot see anything here, so nothing to trace. So finally, to bypass the interaction-based detection system, we first split the existing component into two different pieces and define new interaction among them, and then recover the original relationship between the previous one and the second one. This is the evaluation ratio when you test AVPASS onto the known classifiers against the API transition ratio detection system. When you insert dummy APIs to make a different ratio, we could bypass 80% of cases. And when we modify all the family or package names, we could bypass 95%. 80% seems lower than you expect. Since we limit the number of API insertion to 2,000, so if the malware size is big, it means you should inject more than 2,000 to bypass the classifiers. This table shows the performance of bypassing data flow-based detection. When we inject anti-data flow analysis code, we could only bypass 34%. It's because we only support string and cursor data type obfuscation. And if we hide API name by using Java reflection, we showed that we could bypass 100%. And for the case of interaction-based detection, we could successfully disguise the 100% of malware. As you can see, the success ratio is very low, and the anti-data flow analysis code is difficult to make. So it means if the antivirus company can adopt the data flow analysis within a short amount of time, it means from the adversarial point of view, it's difficult to bypass this analysis. Let me show a demo how to bypass well-known detection systems. Now bypassing API-based detection, and we are launching the classifier and input one malware 149. Now this classifier is extracting malware's call graph and calculating transition ratio between previous API and the second API. And now this classifier is loading already trained model, and this model uses 3 nearest neighbor, and initial classification is malicious. And to bypass this classifier, AVPASS tried to find one nearest benign application. And after calculating the difference from the current malware and the closest benign application, it started to inject the API. It took about 3 minutes, and after the injection process, it can bypass the classifier. And you don't know what's the difference inside. So let me check how the transition ratio changed. At the bottom of the line, you can see the Android util. The number is 19 here. And as you can see, after the injection process, AVPASS automatically inject Android util about 2,000 times, and then eventually bypass that classifier. The second demonstration shows how to bypass data flow-based detection. First, try to analyze this classifier. Try to analyze all the suspicious data flow inside of application. It took about 20 seconds usually. Okay, let's check discover the flows and sequences. So this classifier detected many sequences and flows. If we filtering only the flow, there are still 4 suspicious flows here. And if we feed this flow into the classifier, we can see the classification result. Okay, checking the output, and it is classified as a malicious software. And now let's inject anti-data flow analysis code. Copy the original malware to the AVPASS, and AVPASS try to inject anti-data flow analysis code for string and cursor data type. Now it's done. So copy back to the classifier. Okay, now let's try to extract another suspicious data flow sequences of obfuscated application. And let's check the suspicious flow. As you can see, there's nothing found from the data flow analysis. And if we feed nothing to the classifier, it shows error because there's nothing in there. Now let's bypass interaction-based detection. This process tries to extracting the signature of one malicious software. And it takes more than 3 minutes. After extracting suspicious signature from the malicious software, and then it tried to compare the extracted signature with the originally found malware's signature. As you can see, the matched result is 1, the successfully matched. It means this signature is matched with the malicious parent. And let's split the components and define new relationship. It's done. Copy back to the classifier. Now the classifier is extracting another signature and try to match the signature with the malware's signature. As you can see, the result is a failure. So it means the obfuscated binary is not malicious anymore to this classifier. Now let's move on to the real-world detection system. We set up the target to virus total. Virus total is the aggregation of many antivirus products. And if you upload your malicious software into the virus total will give you the test result of more than 60 antivirus software. So one uploading can get the many antivirus software's result. Since we don't know the internal of antivirus system, there are many questions. Which features are important and which combinations affect to the result, and which classifier they are using now, and are they robust enough to detect variations? This is our strategy to answer these questions. We infer each feature's impact first. By obfuscating individual feature and then query, we can know that which feature is important and which feature is not important. And after we know the feature importance, we could generate all possible variations by using important features and then query to the virus total. At the same time, we need to reduce the number of query because the query is cost in terms of money, in terms of time. So we grouped similar or relevant obfuscation into the same obfuscation group. To provide a way to query safely, we queried by using fake malware, not the real malware. Inferring feature is simply saying that knowing what AVs are looking at now. And this is process for eliminating unnecessary obfuscation. Even though we can think about 100 different features to obfuscation, if antivirus doesn't care about that feature, it means we don't need to obfuscate that features. Since we don't know internal of antivirus software, we need to first guess possible features. For example, byte stream or hash of image or IDs in the resource, APIs, or its argument or number of argument. After we guess the feature, we obfuscate individual feature and analyze the result and impact of that features. These are the feature lists that we found. We found 5 strong impact features for the antivirus and 3 normal impact features and 2 weak impact features. It is hard to tell the number because sometimes 2 weak impact feature, if we combine 2 weak impact feature, the impact could be strong for some antivirus system. After we infer the feature of antivirus, we could infer the detection rules of antivirus systems. So this process is for finding detection internal rules. Someone asked this question. Why do you want to infer? Why not just obfuscate everything and send it to the virus total? Then you can bypass, right? The inferring process is to bypass with the minimum obfuscation and to generate disguised malware with essential obfuscation. After we know the essential obfuscation group, we can make all the variation by obfuscating essential obfuscation. So how? We obfuscate individual features and query all the variations. For generating our variations, we use the 2K factorial experiment design, which is with the K number of features, we decide either maintain case feature or obfuscate case feature. So for example, as I mentioned before, we grouped obfuscation group into 7 different categories. Since we are using 7 different groups, now the number of variations are 2 to the 7. It means 128. If we test with 100 malware, it means 100 malwares and multiply by 128 variations. And since virus total care the upload as one different query and getting the result as different query, it means we needed to use about 25,000 queries to get the result tested with 100 malware. And introducing our difficulty, luckily we got academic license from the virus total, and maximum number of query was 10,000 per day. So it means we needed to take 3 days for one experiment. So if we messed up one experiment, we needed to wait for another 3 days. It was painful working, actually. This 2 table shows example of inferred feature of antivirus solution. The table on the left shows weak detection antivirus, and table on the right shows strong detection antivirus system. What this left table saying that is, if we make only 7 different variations of original malware, it means you can bypass that specific antivirus system with 100% guarantee. And this strong detection system, as you can see, has 18 different rules. We cannot bypass them all eventually, actually. And as you can see, when we bypass that classifier, we needed to obfuscate several features at the same time. These are the observations. We found that most AVs use we define the 7 groups features when they detect. And the sizable imported rules are about 30% of all possible combinations. And better AVs have more complicated rules, obviously. And then let me introduce how to query safely. As a malware developer's perspective, developer should minimize the sending information because the code developed is valuable for the developer. And developer should not send the real code and instead send similar one if the detection result is the same. And the developer doesn't worry about the APK's functionality when querying because he only needed to know detection or bypass. This diagram shows how imitation mode works. Imitation mode is mimicking malware when querying, and the benefit of imitation mode is query without sending entire code. As you can see, the obfuscation group 3 still contains malicious feature inside. And we made imitation mode 1 having obfuscation feature 1 and 2. And since there's no malicious feature inside, it classified it as a benign. And as you can see from the imitation group 2, since this group has malicious feature here, group 3, it is classified as a malicious software. We use the APIs in the group 7. It means without sending your API information to the antivirus company, you can still get the malicious or benign information. This is one scenario for malware developer with AVPASS support. The malware developer developed original malware and started to obfuscate and change it to the obfuscated APK by using the imported features and rules. And with the support of imitation mode and developer's modification, the developer can get disguised malware and eventually can bypass the classifiers or antivirus systems. This table shows the evaluation result of AVPASS. As you can see from the table, average detection without obfuscation was about 65%. After we apply AVPASS, we could reduce the detection to 5.8%. We also find interesting features when bypassing or intentionally being detected by the classifier. To bypass, API is the most important feature, and package name and class name is second and third best one. If we wanted to intentionally detected by the antivirus system, string and API package names are important features. This table shows the impact of import rule combination. This experiment is done in May. As you can see, when we applied only the import rule to bypass the classifier, the bypass ratio is similar with the full obfuscation cases. And the last table shows the imitation mode detection. The full obfuscation the detection was average 8, and after we applied the imitation mode and generated the two feature combinations, this imitation mode shows similar detection ratio with the full obfuscation cases. This is interesting question. Why not 100% bypass? Because you are obfuscating almost everything, but still, why not 100% bypass? The main reason of not having 100% is that obfuscation cannot modify some content inside. For example, of a permission. To guarantee the original functionality of the APK, we cannot modify its permission. And to guarantee the original interaction between components, we cannot modify the intent filter. And AVPASS might miss possible features that AV is used now. And for either case, imitation mode will tell you about the detection. These are the findings of antivirus systems. We found that our conclusion is that there is no dynamic analysis detection for the Android malware system. Heavily depend on the static analysis. And AVs are still detect antivirus system malware by pattern matching. And they don't use data flow or they don't use interaction-based analysis. And 50% of AVs heavily depend on the hash of files. It means if you unpack or repack the malware, you can bypass 50% of antivirus system. And this Lab and White Armor showed the best detection in May. And after we apply Java reflection or advanced string encryption, the Quick Heal and White Armor shows the best detection ratio. We was curious after we get detected from these companies. So we sent an email to the company to ask about how could you detect well. And this company sent no response, and this company also didn't respond to our question. And this company simply says that they are using composite model, and they refused to provide additional information. So it means antivirus company don't want to release any information to the public. They wanted to hide the internal logic. Now let me show you demonstration, starting from how to obfuscate individual APK, inferring feature and rules of AVs, and how to bypass after having the features and rules. Now starting from one malicious software, famous malicious software, LifeMon family. First, you needed to set up the configuration. We already defined several modules here, and you can choose and put into the obfuscation list. and then run the script that we provided. After a few minutes, you will get the obfuscated APK here. And then by using ViralTotal API, you can query to the ViralTotal and get the result and store to the JSON format. If you read inside of JSON, you can see which AV is detected or which AV cannot detect this malware. So how much AV has bypassed? It gets detected 1 out of 62 different antivirus systems. And let's check which AV detected. Okay, you can see which AV had detected your obfuscated binary. Now let's move on to the inferring rule. You can also define inferring list by using different feature set. And then you start to generate variations. Since it is mass operation by lighting, it will take hours. Or if the malware size is big, it will take several days. Because you are compiling each malwares. After several hours or days, you will have a massive number of malicious software. And then send them all to the ViralTotal. And since you have to upload everything, it will take several hours. After you get the result, you can infer the detection rule inside. So this table 0 or 1 means the case whether you bypass or not. It means this antivirus shows some simple rule. This antivirus has more number of rules when they detect. And AVPASS store this information into file. And by using this inferred rule and features, now we can do targeted obfuscation to bypass a specific antivirus system. These are the lists that ViralTotal supports now. We can selectively choose which AV is bypassed. And then we generate all the bypass cases. Now, final phase is imitation mode. After you deploy your malware to the victim's mobile phone, you have another chance to check the detection by generating 2 feature combinations and multiple number of these fake malwares. You can send it to the ViralTotal again. And get the result, which AV is still detecting your malicious software. And if you read the name of file, it will tell you which feature is still detected by this software. And after developer modify that feature and test again using the imitation mode, he can eventually bypass this antivirus system. This is discussions. So from the adversarial point of view, which AVs are difficult to bypass? Obviously, antivirus systems with thorough analysis and pattern matching is difficult to bypass. And we show that stronger AVs checks more features and signatures to detect malicious software. Antivirus with complex rule combination shows good performance. And data flow based and interaction based detection shows it's difficult to bypass from the attacker side. Right now, AVPASS can bypass them by injecting our code, anti-analysis code, to the middle of a malicious software. But our pattern in the AVPASS is too much obvious. And the other problem is that it is difficult to redevelop the entire analysis code. So it means if an antivirus company can develop a faster way to detect, a faster way to use data flow-based one or interaction-based analysis, it is difficult to bypass from the attacker's point. We also compared our obfuscation with the de-obfuscation tools. There are several researches to recover the obfuscated binary into the original one. And this service dguard uses statistical based analysis approach and try to match with any existing class with the obfuscated class. So after we test our obfuscated binary with the dguard, and we showed that we observed that the dguard can recover 70% of class names. And when we use Java reflection, dguard cannot recover any class names. These are the defensive measures from the antivirus company or the virus total side. We think that additional category of return value, for example, not valid flag, will mitigate this problem. Because when we try to infer the feature or using the imitation mode, some of the APKs or all of the APKs from the imitation mode is not valid. It is not runnable on your mobile device, not on your emulator. So if the AV detects not valid or looks malicious software, the AV company can simply return not valid flag, not just telling benign or malicious. Second, we think increasing the number of features for detection will mitigate this problem. The reason why imitation mode work is that if there is any small chunk of suspicious string or suspicious method is included in the fake malware or any fake file, the antivirus always detects it as malicious. But if every software can detect by observing multiple suspicious features and then can conclude it as a malicious, it will also can mitigate the inferring problem. Finally, we also wanted to indicate the active intervention of a middleman. In this case, the middleman could be the virus total. And since they are the gatekeeper, or since they are a gateway, they can monitor the traffic. And if there is some similar query effort from the same user or same place, IP, they can detect inferring behavior and then impose some penalties, such as time delay or refusal to answer or warning message. And of course, our tool has limitations, several limitations. AVPASS cannot obfuscate malware with payload. Some of malware has dropper or native library inside for the malicious behavior. So since we cannot handle this case, we recommend developer to develop all the code inside of your class, not the external file, and then ask AVPASS to handle the obfuscation process. This is another concern about AVPASS. AVPASS can be a malicious pattern after we releasing our toolbox to the open source code. The name encryption is generic and difficult to detect. However, the code injection is already fixed as a template, so it could be malicious signature. And the other problem is difficult to redevelop. For example, over here, this is template for the imitation mode, and there was nothing. Only the name was a hello world, and there was nothing. And after we perform massive number of experiments, they classified it as a malicious software. After 2 months, more companies share the signature as malicious, even though there are nothing. And dynamic analysis can mitigate the obfuscation effort. And there are still fail to learn exists after some incremental obfuscation, and we are handling these issues. Actually, we are conducting two different researches. We separated the research into attack and defense. In our side, AVPASS concerned how to bypass the antivirus system. And defensive side tried to detect malware variations. So as a result, our joint partner Intel Labs developed the Android malware detection platform by incorporating both static and dynamic analysis. And they use emulation-based analysis, and they can reveal some of obfuscations. This is a demo for the Intel Android malware detection platform. Once you sign up and log in, you can upload your malicious software and then select your classifier and then query and get the result of a malicious or benign with the emulated result. Future work. We will introduce more sophisticated obfuscation and we will do more tests. We are planning to test our AVPASS on the Google Verify app functionality and other independent AV solution. And since we are separated with the offensive and defensive side, we will incrementally improve our bypassing ability. And finally, we are thinking about targeting on Windows malware detection system. Now AVPASS is available now. You can go to this website and download the Toolbox. And Intel is also opening the platform to the public. You can send the email to this address, and then we will let you in, and we will let you use this platform. These are the main contact points. You can ask me any question regarding this Toolbox. In conclusion, so we bypassed most of AVs and found a limitation. The case we cannot modify anymore. And we discovered the AV's features and rule combinations. And we proposed the imitation mode to prevent code leakage problem. And finally, we provided the AVPASS as open source. That's it. Thank you for listening to the presentation. How many minutes do we have? 2 minutes? Okay, we have 2 minutes. If you have questions, you can ask me anything right now.
Hi. Yeah, I'm wondering, what do you think is the bigger message of your research, other than, let's say, there are techniques that can bypass AV, which I think everyone knows and everyone presents their own tool.
Right.
So is there something about the way you're doing it that you think is something the way actual threat actors in the wild will do it? Are your methods harder to write signatures for than a myriad of other potential ways you can bypass AV? So I'm just, I guess my question of, is there more to it than just a one-off, demonstration that you can bypass AV?
Okay, we just not wanted to show the bypass. Since now there's a security community only focusing on high ratio of detection and try to decrease the ratio of false positive. But our concern is that the security community do not consider the robustness of detection. So we wanted to show that if we make any variations of original malware, and we showed that we could bypass the classifier, very good performance classifier. So to long story short, our message is that now is the time to think about making robust classifier, not the high performance classifier. Okay.
Hello. Hi, I noticed they used Virus Total, which is using actually Windows-based command line scanners. Do you have any plans to actually implement doing a test using actual products installed on a mobile phone?
What is Acrobat?
No. Actual tests using an actual product on a mobile phone.
So actually we chose several next targets for testing. There are pure AI-based antivirus solution which operate in the mobile system, and Google Verify application functionality is already also worked in the mobile phone. And so, yes, right. So we are planning to do a test more on the more inside of a mobile phone. Okay, right. Thank you for attending.